Hi everyone, we are Dongguan
and Ensu.
from KAIST. Today we are going to present how to systematically analyze cellular layer 3 protocol messages implemented in baseband software based on the specification. This is a joint work with Churjun and Professors Insu and Yongdae. Recent smartphones have multiple processors. The application processor runs mobile applications with Android or iOS. Meanwhile, the baseband processor manages the actual cellular communication. It receives and processes radio signals between the base station and smartphone in real time. Therefore, if baseband is compromised, an attacker can manipulate all communication data. The baseband processes the control plane protocols. The cellular protocol stack, especially the layer 3, includes various core procedures such as phone calls, mobility, or session managements. In the implementation of this layer 3, multiple vulnerabilities have been found. However, analyzing the security of those protocols is not easy, because baseband vendors do not release their implementation details. Therefore, researchers try to manually analyze the baseband or dynamically analyze it considering the baseband as a black box. These approaches, however, suffer from two major challenges. First, manual analyses have limited scalability and applicability. There are over 90,000 functions for processing hundreds of messages, and also it is hard to analyze numerous smartphone versions or models. Second, automating the analysis is not easy. There are numerous non-trivial operations in the core procedures. Therefore, dynamic analysis focuses on finding only shallow bugs such as a crash. To address these challenges, we interpret baseband in a new perspective. Baseband is software for network communication, so it receives radio signals and decodes received messages. In this procedure, the decoding logic should implement the protocol specification, and implementing hundreds of messages can also produce many errors. To implement the protocols, developers first read the documents and implement message structures. Then these structures are used in the decoder function. Implementing the message structures can produce syntactic errors, and implementing the decoding logic can produce semantic errors. From this perspective, we propose BaseSpec. We believe that message structures in baseband software are embedded in a machine-friendly form, and therefore the structures can be easily compared with the documented specification, and this comparison can also be automated. In addition, as the main decoding logic rarely changes, once the baseband is analyzed, we can automate the analysis and apply it to many other firmware images. This is the BaseSpec Overview. First, BaseSpec extracts message structures by parsing the specification documents. Second, it extracts message structures and decoder information from the firmware. Then it syntactically and semantically compares the extracted information. Finally, BaseSpec reports the mismatch results, and then we analyze their implication. Except the initial analysis and implication analysis, all procedures are automated. Therefore, BaseSpec significantly reduces the analysis efforts. To extract message structures from the specification, we first download the documents from two websites. Then we convert the documents into a raw text form. Here, we use the two different websites to address problems in the raw text conversion. As the documents are manually written in a natural language, we should remove inconsistencies in them. Then we parse the message structures. We focus on standard layer 3 messages which have a standardized format. A message consists of a set of fields which is called information elements, whose short form is an IE. IEs can have three elements: IE identifier, length, and value. Of course, IEs can be either mandatory or optional. Each message structure is specified in the document. For example, this figure is the structure of the attached reject message captured from the document. Each row represents each IE, and the presence column shows whether IEs are mandatory or optional. Optional IEs must have an identifier to distinguish themselves from mandatory ones. IEs can have several formats, where TLVE defines the format. By parsing each table, we can extract all message structures from the documents. Now we extract message structures and decoder information from the firmware. As baseband vendors do not release the details, we need to once analyze their firmware. We selected 2 of the top 3 vendors and analyzed the firmware. From the analysis, we could obtain the information of decoder function and message structures. This analysis can be automated because firmware images within the same vendor shares similar characteristics. To analyze firmware, we first extract the firmware image. Baseband software works as a single binary as a real-time operating system. Therefore, we analyze its memory layout and identify function boundaries. Then, we find the decoder function utilizing debug information. For example, in the right figure, there are multiple debug strings, so we searched words like L3 or EMM. After we find the L3 decoder, we figure out how the message structures are embedded. For example, in the case of vendor 1, the message structures are embedded with 4 types of lists. First, it searches the target protocol in the protocol list, and it follows the pointer to the message list. Then it searches the target message in the message list, and it follows the pointer for the IE list for that message. Finally, it fetches the detailed information of each IE, such as IE format or length, from the global IE list. By following these steps for all messages, we could obtain all message structures from the firmware.
From now, I will explain how we compare the message structures. We first syntactically compare the structures. That is, we check whether the message structure in the firmware are correctly implemented as defined in the specification. Through this syntactic comparison, we can find developers' mistakes while embedding the message structures. In detail, we compare the list of extracted IE information from the specification and firmware. If an IE exists in both parts with the same length, it is correctly implemented. But if the length is differently defined, it is called an invalid mismatch. If an IE does not exist in the firmware, it is called a missing mismatch. On the other hand, if an IE exists only in the firmware, it is called unknown mismatch. In this way, we can find 3 types of mismatches between the specification and firmware. Although syntactic comparison checks the correctness of embedded message structures, the decoder function can also have errors. Therefore, we semantically check whether the decoder function operates correctly with symbolic execution. From this analysis, we can find missing logic of the decoder or exceptional cases. In detail, we learn symbolic execution on the decoder function. By defining the input to the function as symbolic, we can collect symbolic variables and constraints which are created when the decoder checks an IE identifier or a length value. Therefore, by analyzing those symbolic variables and constraints, we can identify the message structures that the decoder actually accepts. Then we compare these message structures with the specification to find mismatches. Lastly, BaseSpec reports 3 types of mismatches. Then we analyze their implication. Missing or unknown mismatches can cause functional errors, and invalid mismatches can cause memory corruption vulnerabilities such as buffer overflows. Some mismatches may not cause errors if there is an additional check after the decoding process. Also, as some optional features may not be implemented. Therefore, we should manually analyze the implication of mismatches. Meanwhile, mismatches can pinpoint which part should be analyzed. We implemented a prototype of BaseSpec using IDAPRO and angr. For evaluation, we collected firmware from two major vendors based on the ARM architecture. We tested 18 images from vendor 1 and 3 images from vendor 2. We reported all the findings to the vendors. Here we anonymized vendor-specific information. As a result, BaseSpec reported hundreds of mismatches from all firmware. By analyzing those mismatches, we found previously unknown 10 error cases. For vendor 1, we found 5 functional errors and 4 memory-related vulnerabilities, including 2 critical IC vulnerabilities. For vendor 2, we found 1 memory-related vulnerability. This table shows the number of reported mismatches from vendor 1. Missing mismatches of mandatory IEs and unknown mismatches directly indicate functional errors. Also, hundreds of invalid mismatches showed that the decoder has numerous errors in the length limits. We found that developers try to make additional length checkers after the decoder function, which are very ad hoc patches. Lastly, missing mismatches of optional IEs may not be buggy. Because they are literally optional, developers may not implement them. To sum up, from vendor 1, we found 9 error cases affecting 33 distinct layer 3 messages. As a case study, let's see details of one functional error case and one memory-related vulnerability. This case is a functional error caused by the incorrect order of embedded IEs. While embedding the message structures in the firmware, developers mistakenly put 6 IEs in a different order than they expected. As a result, this caused 22 mismatches, and many messages with those IEs can be decoded incorrectly. Next, this case is reported as an invalid mismatch. We found that one IO of our message is defined as 5 bytes in the specification, but the firmware actually accepts 255 bytes. And there is no additional check for this IE. Therefore, this can cause a stack buffer overflow. As shown in the right source code, 5 byte buffer is allocated in the stack, and the value is copied to the buffer without length check. We found that there is no stack protection, thus this vulnerability is exploitable. Although we built BaseSpec as an automated system, it still requires additional manual efforts for implication analysis. We believe other analysis techniques, such as fudging, can be used to fully automate the implication analysis. Currently, we only analyzed layer 3 messages. However, we believe that our approach can be applied to other protocols in different formats, such as ASN1. Although we found many bugs, we can only cover bugs in the decoding logic, and cannot discover other bugs such as state-related bugs. In summary, we designed BaseSpec, which systematically compares cellular baseband firmware with the specification for standard layer 3 messages. We found 10 error cases, including 2 critical vulnerabilities. From this study, we found that there are many errors in the baseband development process because of the complex specification. However, we showed that such errors can be found through a comparative analysis. In addition, this can be applied to multiple firmware images without real devices. Thank you.
Thank you.